All right, so welcome to the webinar. This will be titled Analyzing the MMS Data with SPEDAS. And the agenda is to cover ephemeris coordinates data, fields data, then EPD data, and plasma data. And the general idea here is to be more breadth rather than depth. So we're going to cover a lot. If you have questions about anything specific, feel free to unmute and ask. And you could also just save your questions until after and ask, or email me. My email is right here at the top. It's actually here twice, egrimes@igpp.ucla.edu. And if you have detailed science questions about the data products, first see the release notes for the instrument you're interested in, and then contact the instrument team. They're the people you should ask about science questions and questions about the data products. I'm mostly good for answering questions about the actual tools rather than the data products themselves, and especially not good at answering science questions. So I guess we can go ahead and get started. So before we get into the ephemeris and coordinates data, I wanted to show off a new tool that we have called MMS Event Search. And this allows you to search the MMS event burst mode events database. So this gives you programmatic access to all of the events that have been uploaded to the burst mode events database. So to run this, you simply just call MMS Event Search with the term that you want to search. And so in this example, we're going to search for current sheet. And so we'll just go ahead and run, or compile and run. And the first time you call MMS Event Search, it's going to take more time than subsequent calls, because it has to actually go download the database and build the database. And there are keywords for returning the details about the events, such as the authors, the descriptions, the start times, and the end times. So you can search for, say, BZ reversal and return all the start times and end times for events that have BZ reversal in their description. And there's also a time range, or a T range keyword for MMS Event Search that will actually allow you to limit the time range. And now you can see it's actually printing out the all of the events that it found that have the words current and sheet in it. And there's a lot of them. And so we can say descriptions. All descriptions should be stored in this variable descriptions. You can see the description has the word current sheet, and you can see the next one. And so that's pretty powerful. So now we can jump into ephemeris and coordinates data. So first off, I'm going to load some MEC data. This is the MMS ephemeris and coordinates data, and I set the data rate to burst, and I loaded all of the probes and set the time clip. But the main thing I really wanted to show off here is var format. Var format allows you to limit the variables that are loaded from the CDF files. In this case, it speeds up the load routine pretty significantly. I think originally it was taking several minutes for me to load all these data. And then I added var format and to only load the position and velocity data for SM coordinates. And it took seconds. You can see less than 2 seconds. And that's because there's a lot of other variables in there that it actually takes a lot of time to actually load all of those variables. And then it takes more time to actually time clip those variables. So var format is super useful. And it accepts wildcards in 2 forms. One are the star, which means match anything, and a question mark means match one item. So in this case, it only matches 1 character. So if there were 2 characters there, the question mark wouldn't match it. And of course, to find the variables that were loaded, you can just use tplot underscore names and see that only the variables with only the SM variables were loaded. And you can go ahead and plot the position. Again, tplot supports the star for matching anything, just like the var format keyword does. And so we went ahead and created this plot, which is the position variables for all 4 MMS spacecraft. And you can notice they're in kilometers. And this is burst mode data, so it's a very small time range. So one thing to note is that sometimes the O4D data actually isn't available. If that data aren't available, you can go to the 89D. The only difference between these two are the magnetic field model that were used for the variables that depend on the magnetic field model. So if you're just trying to load the position and velocity data, there's no difference between the 89D and the O4D. And there are some events where the 89D are available, but the O4 aren't. I think because they had problems generating the Sig-Inigo field model for those times. So if you try to load MEC data and you think the data should be there for the event, try and it's not, try the 89D instead. And just to show it loads the same data. And another useful routine is called TKM to RE. This will actually convert from kilometers to RE, to Earth radii. So you just call it on your position variables. And you see it created 4 new variables, and now with the suffix underscore RE. So these are now in units of Earth radii. So we can plot it. And this time we actually plotted the data in kilometers in the panels, but we used the var form or the var label keyword to set the position along the bottom of the panel, or along the bottom of the panel. So if you look at the bottom where time is, just above it you have the X, Y, and Z components. But unfortunately the labels are messed up here. So to fix that, you essentially have to split the vector into its components and then set the Y title for each individual component. And what that does is that Y title is actually what T-plot uses along the bottom there. So when we plot this time, now we have X, Y, and Z as the proper Y titles in the bottom left. And you can see you actually have the position, spacecraft position along the bottom and the time at the very bottom. So to fix, if you want to bring the time up to the top, we have an option called version. So you just say tplot options version, and versions 6, I think there's versions 1 through 6, and 6 says to bring this time up to the top. So you have all these other variables on the bottom below it. So let's try that. You see now it has the time on the top, and the position variables are actually along the bottom. And if you look at the plot, another thing is in the far right, we put the time and the date that the plot was actually created in the bottom right. To turn that off, you're probably going to want to turn that off for publication quality plots, but it's just a matter of calling time underscore stamp with the off keyword, and you can use the on keyword to turn it back on. So you can see now that the time label is actually gone. And so another useful tool is MMS Orbit Plot. This will actually create the MMS Orbit Plots and accepts all the same keywords, time range, probes, and chord. So for chord, this has to be one of the coordinates that are available in the MMS MEC files. So SM, GSM, GSE, one of those. So you can go ahead and create orbit plots. And you can see now it's in SM coordinates because we set the chord to SM. And we also have formation plots. So if you want to see the actual tetrahedron, you just call MMS MEC formation plot and give it the time at which you want to give and it'll find the time closest to your requested time in the data. And just like the MMS Orbit Plot accepts the chord keyword for changing the coordinates to SM, and I think by default it uses GSM or GSE, yeah. And so we have other options for the formation plots, including XY projections, which actually does the projection onto the XY axes, and the quality, which is really the quality factor, includes the tetrahedron quality factor on the plot. So let's go ahead and plot that. So you can see now we have the projections onto the XY plane. And we also have the tetrahedron quality factor up here at the top, TQF. So I guess we can go into fields data now. So just like with the MEC data, it's just MMS load FGM to load FGM data. We're going to load burst mode data for spacecraft. And just like all the other load routines, probes accepts integers, strings, an array, or you can just give it just a single number. And in this case, we're going to plot. So now we're going to plot the burst mode B field and GSE coordinates. And then we're going to use the var label keyword to actually set the position in RE along the bottom of the plot. So now we have FGM data. And if you look at the bottom, we still have the time on top and then the X, Y, and Z for the spacecraft location along the bottom. So you can see the actual spacecraft location along with the data. And this is really useful for finding out or visualizing where the spacecraft is. And it's probably more useful for fast data rates than burst because the spacecraft isn't moving a whole lot. You can see it's pretty much the same number all the way across for X, Y, and Z. So one of the more useful tools for fields that we have in SPEDAS are kilometer calculations. And we have two different routines for doing kilometer calculations. They were provided by two different groups. One was provided by Andre Runoff at UCLA, and another was provided by Jonathan Eastwood at Imperial College. And they produced pretty much the same results. I think the difference are the units. So one of them is MMS curl, and then MMS Lindegrest. And so we did the calculations using both, and we're going to plot the results using both. And so you can see the kilometer from one calculation on the top, kilometer or the current from the second calculation on the middle, and then I also plotted J parallel. And the big difference here is only the units. See, this is in nanoamperes per meter squared, and I think this is in amperes per meter squared. But they are the same thing. And notice that in this case, the actual Y titles are way off the screen. So if you want to fix that, you can just increase the margin, and that's the X margin. So you just call tplot options and then X margin, and then set the up margin for, and I usually just experiment to find a good margin. It looks like this is pretty good. You can see, you can now see the Y titles. There's plenty of room in the plot. And a new feature that we have is called tplot fill color. That allows you to actually fill the line with the color from the 0 to the line. And so the idea is that you give it the tplot variable name and then the color. And this is an SPD get color actually returns the color index from the current color table that's closest to whatever string you give it. So for instance, we'll just go ahead and notice this is J parallel. So this is actually the variable that's on the bottom here. And notice that it goes positive and negative, but it's hard to actually see without filling the color. So let's go ahead and fill the color. So now we have J parallel with, it used blue to fill the line from the 0 to the actual line. And now you can see see where it goes positive and negative. I think this would probably be useful for, say, BZ. And another thing to note is that SPD get color actually uses the current color table. So if you change your color table, the definition of blue will change with the color table. So this is really very useful. And to see the different colors available, just open it and look at the top. So we have all the supported colors, and should be a lot of them. But again, it does depend on your current color table. So if the color doesn't actually exist in your color table, it'll find the closest one to it. And just like FGM, we can load SCM data, just MMS load SCM. And in this case, I used a different time range, mostly because there's a wave here that you can actually calculate the dynamic power spectra. So this is TD power spec. And I used the defaults from our SCM crib sheet. So if you want more examples for dynamic power spectra, check the SCM crib sheet. I think if you use burst mode data, you probably want to change the number of box points and the number of shift points. So let's go ahead and calculate that dynamic power spectra. You see it created 3 new variables, X, Y, and Z. And so we can go ahead and plot them again. So now I have the dynamic power spectra with the X, Y, and Z. X on the top and Z on the bottom. And of course, you can also load data from DSP. So you can load the magnetic and electric power spectral density from the digital signal processor. And by default, I'm not sure what data types it loads, but you might want to be specific about the actual data types here and the level. And so now we have the electric and magnetic power spectral density from DSP. And of course, we also have the electric field data, that's EDP. We're going to load some burst mode data. And go ahead and plot the burst mode electric field data. So now we have the electric field data. And we still have our position along the bottom here because we're still using that same window. Another thing to note is that when you load the electric field data, we also load the parallel electric field data. And so if you want to visualize the electric field data, the team suggests using the error bars on the electric field data. So you want to actually set these options. And these options are actually directly from the crib sheet for EDP. And so this shows the, on the bottom, we have the parallel electric field data along with the error bars in pink. So there are large error bars here. You should probably contact the team before doing science with these. This was actually a note from the team, is to always use the error bars on eParallel. And another data type available via the EDP load routine is the spacecraft potential. So just set the data type to SCPOT. So that's spacecraft potential. We'll go ahead and load that and plot it on the top. So now we have the spacecraft potential along the top in volts. And finally, there's the electron drift instrument. So that's EDI. So you can see it loaded a lot of variables, and you can plot the E cross B drift velocity in GSC coordinates. It's just the V drift variable. And I included some more crib sheets down here at the bottom that are probably going to be useful. These are longer crib sheets that show how to use, do some more advanced calculations with the fields data. So you can do coordinate transformations. This is the Q cotrans, so this is quaternions. This is coordinate transformations using quaternions. And we have an example showing how to calculate pointing flux and the pointing vector using fields data. And we also have examples showing how to transform to minimum variance analysis coordinates using some of our internal tools. These were all pretty long scripts, so I didn't want to include all of it today, but if you go over them and have questions, send me an email, let me know. So moving on to the EPD, that's FEEPS and EIS. So I'm starting off here with the EIS angle plots. The reason for this is because these can actually mess with your T-plot windows, and I'm going to show some more advanced T-plot stuff after this. So I want to go ahead and get the angle plots up front. So to create EIS angle plots, it's just EIS _ang _ang. And this routine was provided by Ian Cohen and Joe Westlake at Johns Hopkins. And it has lots of options. You can set the species, data units, data level, and output it in postscripts, pings. But by default here, we're just going to use probe 4 for the same probe we were showing before. And then let's So you can see it has the angle plots with pitch angle contours. From the top to the bottom, it has the different energy bins. So the energy bin, the first energy bin's on top, second one, third, and then fourth. And across from left to right, it's times. So first time, second time, all the way to throughout the day. And this is protons, but you can set the other species via keywords. So before we move on, I think that since that messed with our graphics configuration, let's reset, and then now let's load some FEEPS data. So call MMS load FEEPS. And one thing to note is that MMS load FEEPS does a lot of processing behind the scenes. So this is not just loading the CDF files, it's actually removing sunlight contamination, doing flat field corrections for the ions, and removing, doing various adjustments for the bad energy channels. And all of this was changes that were requested by the team and maintained by the team. All right, so we loaded the data. We also do spin averaging as well, in addition to calculating the full omnidirectional spectra. So now we're going to plot the omnidirectional and spin averaged spectra. So the omnidirectional, the standard non-spin average is on the top and spin average is on the bottom. And you can kind of see that if you look. But so another useful tool, this is, we're going to show a lot of examples using flattened spectra, because one thing that people frequently want to do is, instead of looking at the spectra for times or versus time, you want to look at the spectra for a specific time. So to do that, you use flattened spectra. So call flattened spectra, and then it allows you to select the time on the current plot that you want to see the spectra for. If you have multiple spectra, it'll plot multiple spectra. So we'll just select, say, 2200. And it created a plot which should show, so it should show the intensity along on the left axis and energy along the bottom. And it also has the variable names as the legend. So you can see the blue line is the spin average, and the black line is the non-spin average. And if you don't want to have to re-click that time, you can use the replot keyword. So if you forget an option, you can use replot to use the previously selected time. So if you say you want to set the X log, Y log, save the files as PNG, you just calls replot and it'll use the same previous time. Notice at the top here, it has the time still 2200. But this time the plot's actually done on a log scale on both dimensions, on both axes. And you can also specify the time via the time keyword. Instead of actually selecting a time, we're using the replot keyword. So this time we said 2 o'clock, and it created the spectra for 2 o'clock. And you see the time's actually at the top again. And there's also a keyword called bar that will set the vertical bar at, we'll draw a vertical bar at the spectra, or at the time that you created the spectra for. So we have spectra here at 2 o'clock, and if you look at the T-plot window, it should have a vertical bar right at 2 o'clock. Yep. So that's useful for keeping track of exactly where you clicked. And so we also have pitch angle distributions for EIS and FEEPS. So for FEEPS, it's just MMS FEEPS pad, and then you set the options. In this example, we're just going to set probe, but let's go ahead and start running it. And then open it up. You can set, in addition to probe, you can also set things like the energy, to limit the energy range, the number smoothing to do smoothing. And you can also specify, tell the routine to calculate the angles from the actual B field data instead of reading the angles from the CDFs. So you can see it calculated the pitch angle distribution. It also calculated the spin average pitch angle distribution. Again, we use T-plot names to list the actual variable names. So you have pitch angle distribution, the smooth, and then the spin averaged. And so to plot. those. So we have, I think the smooth is in the middle, the spin average is on the bottom, and the full one is on the top. So this is pitch angle distributions. And so, and I wanted to show that flattened spectra actually works here as well. So it's not just on energy spectra, it works on pretty much any kind of spectra. So in this case, we have pitch angles along the bottom and the intensity along the left. And it looks like the units are actually the same, but the labels are different, so it thinks they're different. And we also have EIS, so MMS load EIS, and the data types here are E by time of flight and pH by time of flight. So it's energy by time of flight and pulse height by time of flight. So we can go ahead and load that data. And then we're going to plot the spin average energy by time of flight proton flux. And so we have that. And let's see. So another useful routine is flattened spectra multi. So this is like flattened spectra, except it allows you to plot multiple times instead of multiple panels. So you give it the number of times you want as an argument, and it'll allow you to select, say, 3 different times. So we can select a time at 6, and then let's do 7 and 8. And creates a spectra. Again, for it uses the labels this time as the actual the times. And you can see the 6 is the black line, 7 is the blue line, and then 8 is the green line. And replot works for this as well. I didn't add the example here, but replot also works. It'll go back and use the times as well if you use the replot keyword. Or you can specify times via the time keyword. Just give it an array of times. And you can see it created the spectra again, 6, 7, and 8. This is because I just specified 6, 7, and 8 via the time keywords. And just like FEEPS, we have MMS EIS pad, which allows you to calculate pitch angle distributions. And again, just like FEEPS, there's a bunch of options. You can check the header for the species, setting the energy range, setting the smoothing. You can combine the proton data, so combine the energy by time of flight and pulse by time of flight. I think there's also options to combine multiple spacecraft for EIS. And we can go ahead and plot the spin average, EIS pitch angle distributions. So it's the spin average, and we can, again, flatten spectra should work here as well. So we've got the pitch angle distributions at 3 different times. And see, so some other useful things. I suggest checking the header of flattened spectra for some more options. Let's see. So there's all kinds of tools here. You can move the legend to the left. You can change, say, the window. So what this is actually allowing you to change the time. Instead of choosing a specific time, you can average over a time. Or you can set a number of samples. And you can set file names, set the colors. There's the X values and the Y values. Keywords actually returns the values themselves, so you actually have the values. And I'm going to show some more examples with the plasma data. So we're moving into FPI and HBCA now. So for loading FPI data, it's just MMS load FPI. The one thing to really note here is the center measurement keyword. You really want to center the measurements for FPI and HBCA. The issue here is that for most of the MMS instruments, they're actually at the middle of the accumulation interval. The measurements are at the middle of the accumulation interval. But for FPI and HBCA, they're at the beginning of the accumulation interval. So you have to give it center measurements if you want to actually compare this with data from the other instruments. And the data type here, we're setting DIS moments and DES moments. So that's the moments data from for electrons and ions. So we can go ahead and load this data. And then we're going to plot the number density for electrons and ions along with the error flags bars. And the error bars are very useful for figuring out potential issues with the data. So yeah, you can see there are radiation issues later in the day. You can see where you would need to, you might need to contact the instrument team before actually analyzing or trying to do science with any of the data in some of these areas. And just like FPI, we have HPCA, and again, center measurement's pretty important when loading the data. And the data type is different here. For loading moments data, it's just moments, and loading the ion distribution data, it's just ion. But other than that, all the keywords are the same. And I did originally had time clip on all of these, but it was taking so long to time clip. One thing that I didn't note or didn't mention earlier is that when you call these load routines, it's going to go out and grab all the data it can find within around that time range, and it might include data outside of the time range slightly. So if you want to get exactly the time range that you requested, you have to add the time clip keyword. And the downside of that is that it can take a lot of time to actually time clip the data. In fact, it can take significantly more time to time clip the data than it actually takes to load the data and the variables. Just because there are so many different variables that need to be time clipped in a lot of these files. It's taking a while to load this, so I guess we can also mention the ion data for HPCA is actually stored with full angular information. So you can't actually, when you load the ion data for HPCA, you can't just throw the T-plot window to T-plot and ask it to plot it, because it has the full angular information, and you have to actually calculate the omnidirectional spectra by summing over the A nodes and then spin summing. If you don't spin sum, then you're in this case, you're only getting half the distribution, because the actual, I'm going to show later angle plots that show this issue, but you have to spin some to get the full omnidirectional spectra for HPCA. And so the data should be loaded. And these routines for actually calculating the omnidirectional spectra have more options, like say field of view. It's for if you want to limit the field of view. If you want to give it full field of view, it's just 0 to 360. But if say you want to have half the field of view, it's just 0 to 180. I think usually people do the full field of view. And you can see it creates the variables. And so these H plus flux variables are the variables with the actual full angular information. So if you tried to plot that in T-plot, it wouldn't work. And after we're finished doing the A nodes, we're gonna spin average. And the routine is called spin sum, but there's a keyword average to actually do the spin averaging instead of just summing. And then once those calculations are finished, we're gonna plot FPI ions on top, HPCA ions below that, and then EIS ions on the bottom. there. All right, now we can plot it. We should have, yeah, FPI on top, then HPCA, then EIS. And so notice that the units on all of these are different. So FPI has EV on the y-axis, HPCA is EV on the y-axis, and EIS is KEV. And also in the actual units here, this is KEV per KEV, then we have per EV, and then per KEV, and then per KEV. So all these units are different. So when you call flattened spectra on this, you're going to get different units, right? So we have keywords for fixing that: 2 flux and 2 KEV. So what that does is internally it figures out the units and then converts them to the proper units: 2 flux and 2 KEV. And so now we should have, yeah. So this example, the flux unit, everything was converted to flux on the y-axis, and everything was converted to KEV on the x-axis. And you can see that seems like the unit conversion actually worked. Another useful thing is to actually set the legend name. So that's legend underscore name. This is a new feature just for this. If you set that option and then call flattened spectra, it'll use that legend, that name on the legend instead of the variable name. So now we have the black line is FPI, the blue line is HPCA, green line is the pulse height by time of flight for EIS, and the red line is the energy by time of flight for EIS. And another very useful feature is T-plot multi-axis. This allows you to plot 2 data products in a single panel with the axis on the left being different than the axis on the right, so different axes. And in order for this to actually work, you really want to remove the labels and set the colors. So to remove, the issue here is since the labels would overwrite or essentially be overplotted over one of the axes, so you wouldn't want to overplot labels over an axis. So to create a multi-axis plot, you just call tplot multi-axis. And the first argument is the arrays, or an array of the tplot variables that you want to have the axis on the left for, and then you give it the array of tplot variables you want to have it the axis on the right for, and then you give it the panel of the right plot. So this is probably just easier to just show an example. I'll go ahead and plot it. So you can see in this example, we plotted, see the density for DES on the axis on the left, and that's a black line. And then we have the temperature for DES with the axis, and that's blue with the axis on the right. So these are actually on completely different axes. And again, the reason we removed those labels is because the labels for these variables would be popping up, would be over here. And you can also plot line plots over spectra. So in this example, we plot number density, the bulk velocity, and then the omnidirectional spectra. And then we plot the perpendicular temperature over the spectra. So number 3 means overplotted on that third plot. So let's try that. All right, so again, we have the density on top, velocity, and then spectra with the temperature on a different axis. And one thing to note is that the color bar here is actually, it's still here, it's just off the screen. So if you increase the X margin, you can get that color bar back. It's just right off that screen. So getting the color bar back is just a matter of increasing the X margin here. And so in addition to all this moments data released by the team, they also released the full distribution data for FPI and HPCA. So we can actually calculate energy spectra, pitch angle distributions, gyro phase distributions, etc., using MMS part get spec. And what this does is calculate those spectra directly from the distribution functions themselves. This provides lots of options, allows you to limit the energy range, limit the pitch angle range. So this adds flexibility to actually allow you to calculate spectra. And there are lots of options here. If you're familiar with MMS part products, This is simply a wrapper around MMS part products that loads the support data and then calls all the sets all the options and generates the spectra. In this example, I'm only showing the energy spectra and the pitch angle distribution for FPI ions. Again, there are many options here for the output options. You can do, there's a multi-pad option, which allows you to generate the pitch angle distribution at each energy. And then there's an MMS part get pad that allow you to actually generate the pitch angle distribution over energies using that multi-pad option. So if you're interested in generating the spectra from distribution functions, look at the header of MMS part get spec first, and then look at the header of MMS part products, because all of these options are also passed MMS part products. So all this options should be supported. For instance, you can subtract the bulk velocity, subtract the error from the distribution data prior to creating it, subtract the spin tone from the bulk velocity prior to actually subtracting the bulk velocity. I can generate moments, theta and the phi spectrograms, and all this can be changed. You can actually set the species for any valid species for HPCA or FPI. Let's see, this should be almost done. Let's see, another keyword I threw on the end here is SPDF. So all of our load routines actually accept the SPDF keyword. If you're on the East Coast, you might want to set this keyword. What it does is tell the load routine to download the data from SPDF instead of the LASP SDC. So if you're actually at Goddard and you're downloading the data, you probably want to set the SPDF keyword just to download it from the closer source. It'll probably be a lot faster if you're at Goddard. Another thing we can do is go ahead and open MS part products and show the header. This is where I go if I need documentation on MMS part get spec. So you can actually limit the gyro phase range, you can limit the pitch angle range, you can limit the theta range, the phi range, the energy range, and there are lots of options. Looks like it's almost done, 45%. It's just taking a lot longer than it did yesterday. But the cool thing here is after you generate the spectra, you can actually compare the spectra that you generated with the spectra from the moment CDF files. So you can prove to yourself that you're actually generating the same thing that the team is generating using our tools. And they're actually generating these things different with using their own tools. So these things are independently being calculated. So it's good that they match. And we might skip the HPCA MMS part get spec because it basically does the exact same thing. It's probably going to take even longer. But in order to do that, you set instrument equals HPCA and set your species. By default, it's going to use H+, but I wanted to show that it's an option here anyways. You could set it to O+ and generate the O+ spectra. All right, so we now have the pitch angle and the energy. So let's go ahead and just energy spectra on top and pitch angle distribution on the bottom. And for, I think this is 20 minutes of data. And So in this, now we're going to plot the energy spectra calculated from MMS part get spec on the top, and then the energy spectra released in the FPI CDF files on the bottom. And so if you really want to compare them, you have to use T-limit to zoom in. So it's just called T-limit. That allows you to select the 2 times on the plot to actually zoom into. So let's zoom into this time up here. And so now you can see the spectra generated directly from the distribution functions on the top matches the spectra released by the team on the bottom. So another useful tool is the MMS part slice 2D. So these are the 2D slices of the distribution functions. And so if you're familiar with SPD slice 2D, MMS part slice 2D is essentially a wrapper around SPD slice 2D. So it goes out, loads the support data, the B field data, and calls SPD slice 2D. It also calls SPD slice 2D plot to create the plots. So MMS part slice 2D does all the work of actually creating the 2D slices. So you should be able to create a slice just by setting or calling this routine with setting with all the appropriate options, which means it accepts a wide range of options. Basically all the options for the plot routine, as well as all the options for the SPD slice 2D routine. So setting the E range, the resolution, changing interpolation, it's all available via keywords to MMS part slice 2D. So here's the FPI distribution function. And this was just a slice, and this is in VX across the bottom and VY on the top, and for ions. And of course, it also works for HPCA. Just set the instrument to HPCA, species to H+. I think by default, it's going to use H+ anyways for HPCA. Of course, you can use O+ for oxygen. And here's HPCA, H+, and XY. And I mentioned this earlier, but it's worth noting again that MMS part slice 2D accepts all the keywords of slice 2D and SPD slice 2D plot. So it's rotation, custom rotation, background color index, background color RGB units. So instead of plotting the FPI distribution function, we can plot the FPI units and energy flux. And we can set the background color to, I think this is gray. It's a light gray. And I also listed all of the possible different types of rotations via the rotation keyword down here. So lots of field aligned transformations can be done internally, and all you have to do is just set the rotation keyword, and it'll go out and grab the support data and do the calculations and create the plot. And another useful thing is samples. It's not just samples though. There's actually many ways to set the actual time range, the number of samples, how to do averaging. All of those are options to SPD slice 2D that you can set. So in this case, we set the background color to light gray, and you can see the energy flux. The units were converted to energy flux. And this is the FPI and VX versus VY. And so we can also do HPCA. And this time we're going to set samples equals 10. So if you look at the top here, it has the time range, which is 12:10:25 to 12:10:30. So it's just one sample for FPI. In this case, we're going to do 10 samples. So there should be 10 samples for HPCA. And we also set the units to E-flux, so it should convert the HPCA units to E-flux here as well. And so there it is, the HPCA H+. And if you look at the number of samples, it actually used 10 samples, and it's 1209 to 1211. right, so another useful thing is to actually combine these energy spectra, time varying T-plot windows and moments with these 2D slices. So for that, we have a routine called MMS Flipbookify. So what you do is create a window and then create a T-plot. So we have the T-plot window, and we have FPI DIS data, the density on the top, velocity, and then energy spectra. And so we have this routine called MMS Flipbookify. What this does is it takes this current window and then adds the slices, 3 slices to the right-hand margin. That would be, by default, I think it's Vx versus Vy, Vy versus Vz. We'll see once it generates it. Let's see. The big thing to note here is that you have to set either time step or seconds keyword if you have high resolution data in the top panel, because by default, it's going to use the time steps and that variable at the top panel to actually generate the slices at each point. So when I say seconds equals 60, that means generate the slices at each 60 or every 60 seconds. And I think the rest of these keywords are normal keywords. So we have the instrument, set it to FBI, set the species to I, and probe, and all of this gets passed to the SPD slice 2D routine internally. And finally, we have the video keyword, which actually combines all this into a video, which I'll show as well once this is done. So right now it's looks like it's loading the data. And one other warning is that you might, depending on how big, how many panels you have here, and I think essentially your window size, your display size, screen resolution, you might have to experiment with the window X size and Y size to actually get your plots to come out correctly. And so now it's generating the slices. And so it moved the panel over and then added the slices to the right-hand panel. So you have Vx versus Vy, Vx versus Vc, and then Vy versus Vz. And so there's also a keyword to MMS Flipbookify called rotations. It actually allows you to change these rotations using the rotations available via the rotation keyword. And you notice that it's adding a vertical line at each time step where it's drawing or where it's calculating the slices. And then finally, it really should be, yeah. So it's creating this movie as well as it's generating this. And so I created this plot using just 3 random panels for FPI data. It's worth noting that the T-plot window can actually contain anything. You could plot DST and have it all energy spectra or all line plots. It can really be anything, and it'll just, the MMS Flipbookify will create a margin on the right-hand side and add the slices. It also accepts, I think, units keyword to actually change the units. And just like before, if you want to look at all of the options, just open up MMS Flipbookify and look at the header, because there are tons of options for controlling just about everything. You can even change the frames per second in the video. And it's worth noting again that I mentioned it earlier, but it's definitely worth noting again that the default timestamps are taken from the first panel in the window. And if it happens to be a full day of survey mode FGM data, that'll produce 1 million plots, 1 at each FDM data point. So you definitely want to use time step or seconds keyword to actually avoid generating millions of plots accidentally. Right, so it generated all of those flipbookify plots. So now we should be able to run the video. You can see we got the slices evolving over time, along with the vertical line at the point where the slices were taken. And so we can come back here and just like with FPI, it works with HPCA as well. You just have to set the instrument to HPCA. By default, it's going to use H+, but I specified it here again because you can also change it to O+. And specify the data rate, time range. So in this case, I plotted 4 windows, or 4 panels, actually 5 panels. So there's one off on the right here, yeah. So 5 panels, all HPCA data, and now it's generating the HPCA slices and drawing the vertical line at each point where the slice was taken. And so in addition to the header for MMS Flipbookify, another place to look for examples are the examples folder. We have a crib sheet specifically for Flipbookify, so it's MMS Flipbook crib, but we also have webinars on MMS Flipbookify that we've held previously. And so there's full scripts on MMS Flipbookify in the webinars folder, which is a good time to point out that this script is also going to be in the webinars folder. Actually, it's there now in the latest bleeding edge zip as of this morning. In the project's MMS examples webinars, this one is just MMS analysis webinar and then the date. I try to use this format for all of them with the date at the end. So if you have any questions about the date, about the webinar was held, just look at the very end of the file name. I think there are at least 2 in this folder for MMS Flipbookify because we've held 2 different webinars on that tool. And you can also change the interpolation options for this, but if you change it to geometric, it's going to take significantly longer to do the calculations. Because by default, it uses 3D interpolation. And so now we should have a video for H+. Go ahead and click play. So we see the slices over time. And so finally, we also have angle-angle plots for FPI and HPCA. So for FPI, it's just MMS FPI ang, and you give it the time. And in this case, we're going to say species for I, and set the probe. And I'm requesting a ping. The PostScript also works. You can create PostScript files. So what this creates is angle-angle plots, angle energy plots, and then pitch angle energy plots for FPI. And it's worth opening this to show the header. Just like with our other routines, take the header for various options. You can subtract the bulk velocity. Prior to creating the pitch angle energy figure, you can change the pitch angle energy units. Say PostScript, specify center measurement. This is pretty important. You're going to want to center the measurements, especially if you're going to be comparing to other instruments that already are at the center of the measurement. You change the X size and Y size, give it a suffix. And for the FPI, we actually have all energies, which will generate the azimuth versus zenith plots at each energy. By default, it does the average over all energies. Well, I think it might sum over all energies. So we're looking into whether or not that, yeah, includes all energies. And I probably should have did a full reset session because it's taking forever to load the data. So another thing to note is for FPI, you're going to see on the angle plot, we have pitch angle contours. You can disable that with the no contours keyword. And I actually created these yesterday, so I could go ahead and show. Let's see. I think I stored them in here. Yeah, so this is FPI. This is the figure that I'm actually generating now that I saved yesterday. So this is azimuth flow angle on the bottom and zenith flow angle on the left. So you have azimuth versus zenith, and then the pitch angle contours. And again, this is the distribution function. So we also have zenith versus energy. So zenith on the left and energy on the bottom. And we also have azimuth versus energy. And then pitch angle versus energy. And this is all for FPI. I think it's FPI ions. So this is essentially what these what this call is generating right now, these four figures. And it's taking so long, we might as well move on to HPCA and show off that one. So HPCA, the warning here is that this is brand new and experimental, and there are definitely issues with it right now that need to be fixed. Like right now, it only takes a certain one data point in time, which is not spin averaged. So you're only going to get a limited set of angles here because it's not spin averaged. I'm going to have to update this to actually do spin averaging before it generates the angle plots. But when it works in a very similar way, you just call it MMS HPCA ang, give it the time closest to the time that you want. So the data rate, the probe, the PNG, and it's gonna, by default, it's gonna generate the same file names as MMS FPI ang. I should probably fix that, but for now, I just set the suffix to underscore HPCA to differentiate between the FPI and HPCA. So that's these three figures are generated by MMS HPCA ang. And notice that this one is actually missing the pitch angle energy. We don't have that for HPCA at the moment. I think there might be problems or updates that we need to do for, say, subtracting the bulk velocity prior to doing HPCA angle plots and pitch angle energies plots. Again, this is just a brand new experimental routine for calculating these angle plots. So now that we have the FPI, we can go ahead and, in fact, before I did a full reset session, that way it's faster to generate the HPCA ones. But I already have them here, so we can compare, say, this is azimuth versus energy for HPCA. And notice that there's a wide range of azimuths missing here. That's because it's not spin averaged. We're only looking at half the view here because we're only looking at half the spin. So we're only looking at a single data point. For spin averaging, it would fill in this this part here. And we have zenith versus energy for HPCA. And again, this is only half the spin, but we can compare zenith versus energy for FBI ions. It looks like they're at least seeing the same thing, or at least as far as they can. And then finally, there's the actual angle plot for HPCA, which is azimuth versus zenith. And again, you can see the azimuth's range here is limited by only being half the spin. Once we spin average, it'll actually fill in that part right there. And so that's pretty much all I have for the webinar. Thanks for calling in. Again, this is currently in the Bleeding Edge zip, located at Projects MMS Examples Webinars. And my email is right here at the top, egrimes@igpp.ucla.edu. And a little known fact is you can also email me at ericgrimes@ucla.edu. So if you have trouble remembering all of this, just do Eric Grimes, my full name, at UCLA, and it'll send it to me, same email address. And well, thanks for calling in. And again, feel free to email me anytime, night, day, weekends, whatever, it doesn't matter. I always answer my email. So thanks for calling.